FFT tells you which frequencies are present in your signal, right? So let's take a signal and run an FFT on it. There are many tools out there that enable us to perform a spectral analysis, but I first met the FFT as part of my hobby of sound engineering in a program called Audacity, an open source audio editing package. Here's what happened. I clicked on Analyze and Plot Spectrum and got my graph. But then I noticed I could alter a parameter called FFT size and another called windowing function. I wondered what these parameters were for, so I played with them. Changing the parameters changed the frequency spectrum of my signal slightly. But how could that be? The signal hadn't changed. Why should the way I measure it change its spectrum? If I want to measure the length of a line and I have two rulers to hand, surely it shouldn't make a difference which ruler I choose. Both should give me the same measurement. Unless, of course, there was something wrong with one of my rulers. But here I was, changing rulers as it were, and this apparently changed the frequency spectrum of my signal. Could it be that the FFT is just a bad ruler? If so, why is the FFT the go-to tool for spectral analysis, not just in sound, but in many other fields too? I decided that rather than be a bad workman and blame my tools, I had better learn more about what the FFT does and how it does it. I'm Mark Newman, and for the past 25 years I've been working in the field of medical electronics. The FFT has been an important part of my professional life. It's an amazing tool, but as I've discovered, it's also a much misunderstood one. Now, that might have something to do with how mathematical it is, and although everyone may think that we engineers are brilliant mathematicians, that's not always the case. At least, it wasn't for me. Maths was my worst subject at school. But it didn't stop me from loving electronics. Therefore, I had to find a way to understand the FFT in a more intuitive way. The FFT, or fast Fourier transform, is a computationally efficient version of the discrete Fourier transform, which is a Fourier transform for discrete time or sampled signals. The Fourier transform is a development of the Fourier series, first proposed by the French mathematician Jean-Baptiste Joseph Fourier in 1807. To find out how the Fourier transform works, we first need to understand how the Fourier series works. Fourier's original theory states that
any function of a variable, whether continuous or discontinuous, can be expanded in a series of signs of multiples of the variable.
In layman's terms, it breaks the signal apart into its component building blocks. Just as this Lego car is built out of individual Lego bricks, each brick with its colour, its shape, and its position in the car, so signals are built out of individual sinusoids, with properties like magnitude, frequency, and their position within the signal, or phase. Add enough sinusoids with just the right properties together, and we can reconstruct almost any signal. Take this sinusoid here. It doesn't sound like much, does it? But let's add another sinusoid to it with a different frequency, magnitude, and phase. And another. And another. As I add more and more sinusoids, it begins to sound more and more interesting, until, after adding some 40,000 different sinusoids, it sounds like my voice saying Fourier over and over again. I can therefore describe this signal by adding together lots of different sinusoids, like this. Each cosine term represents a different sinusoid. Here are the magnitudes of each sinusoid, here are the frequencies, and here are the phases. Adding them all together reconstructs the signal. This is the Fourier series expansion of my periodic signal. The signal is periodic as it keeps repeating itself. We'll talk more about that a little later. But have we reached Lego brick level for this signal yet? Or can I break it apart still further?